Hello everyone, my name is Harsha. I'm here to discuss about face recognition using hidden Markov models. This is the overview of my presentation. First, I'll give an introduction about the project I'm doing and my motivation for doing this project. And then I'm going to give a brief introduction for the hidden Markov models and then how we use the HMM to detect the face in the face images and also the feature extraction in the face image such as eyebrows, eyes and nose and mouth, and also uh, and also I'll show you the training of the face models for the system I designed and the face detection and how the system is going to recognize the face which already is in the database and also the conclusions. So, face recognition is one of the important abilities of mankind as well as for most of the beings on this earth. It's a gifted ability for the human beings to detect someone whose face they have already seen. Humans' ability of face recognition is very robust as most of the interactions between human beings are different when they have seen that person in the past and when they haven't seen that person in the past. The robustness of human beings in recognizing distorted images, inverted images, and remembering the images has led to an important research area on the idea that human brain contains a region only dedicated for face recognition. Due to the increasing security issues and threats, and due to the importance of the face recognition and face detection from the live video streaming as well as the regular images, this area has emerged as an active research area. There are many uses of face detection in day-to-day lives. So, for few examples are to maintain the restricted access of people into restricted areas where it can be a security threat to everyone, and also authorized access in the ATM machines, and to recognize people from the existing database at immigration checkpoints, police stations, and banks. These are the most commonly used places for face detection and recognition. An efficient face detection system must perform extremely efficient even in the cases such as two or more faces in the image. In most of the cases, the image processing or the face detection should be done with multiple objects in the surroundings and multiple objects in the background. Those multiple objects can be faces as well. Even during varying lighting conditions and background colors, and to handle non-frontal facial images of all genders. Due to the changes in the background appearance and lighting, changes the face recognition has become a difficult task for the computers. Most of the research on the face recognition is mainly dependent on two approaches. Efficient analysis of geometric features and template matching are two main approaches used for face recognition. In this HMM model for face recognition, the significant areas of face such as hair, eyes, nose, and mouth are processed in a natural order from top to the bottom of the face. In this presentation, I propose a model of face recognition using HMM. So this model uses KLT coefficients for efficiently extracting the observation vectors. Based on the consistency of the previous HMM model for face recognition, an efficient face detection approach is also explained. In the scale invariant systems, the classic template method doesn't provide much flexibility in the face detection and recognition unlike the HMM model. The motivation behind this project is to present an efficient and novel face detection technique using HMM model. This new approach is also demonstrated with various examples and the input images. Another motivation is that it is important to study how the performance and efficiency is affected by varying the parameters of the HMM. The investigation should also be done to show how HMM performance is affected with the changes in the image resolution and by representing the image in the edge domain. So HMM stands for Hidden Markov Model. HMM is mainly comprised of finite number of states. Transition of state between initial state probability distribution and state probability matrix, and also each state has a set of probability density functions which are based on hidden and unobservable Markov chains. The HMM model consists of the following elements. It has states with sequences numbered from 1 to n, and each two states are connected by arcs. So whenever a new state is entered, a new observation is generated with the mean covariance matrix defined as Vj and mean J with the help of multivariate Gaussian distribution. The probability of transition between two states I and j is determined by the arcs, which have probabilities for transitions associated with them. For example, for any state j, the model starting in j would have a probability of pi j. HMM is mainly consists of the following set of parameters, which I explained in the previous slide. N is the number of states in the model, A stands for the state transition matrix, P is the probability function, and pi is the initial state probability distribution. If the set of states can be defined as S, then a state, then the set of states S is equals to S1 to Sn. The probability of the state transition matrix can also be defined as Aij, and the constraints for the Aij are as it's the probability it should lie between 0 and 1, and the sum of the probabilities of Aij should be equals to 1 for n states. The continuous observational density functions are characterized by using the states of continuous density HMM. Mixture coefficient Cik for the kth mixture in the state I is defined as Cik, and n is a probability density function. In the shorthand representation, we can say that HMM lambda is A, B, and pi. Face image HMM. In case of speech recognition and action recognition, the data is one-dimensional, so hidden Markov models were used successfully. In the next sections of this presentation, we discuss the face recognition and face detection for grayscale images using a one-dimensional HMM and also its performance. Even if the images are affected by small rotations and plane of image is perpendicular to the regular image processing, the HMM model for face recognition, the significant areas of face such as hair, eyes, and nose and mouth are processed in a natural order as told earlier, from top to the bottom of the face. Each region of face is assigned to a state in a left to right one-dimensional HMM. The next figure shows the transition of the probabilities Aij and the state structure. We can see the transition from hair to the mouth, that is from top to the bottom. The next step is feature extraction. Each input image of height h and width w is segmented into blocks of width w and height l. Most of the all the consecutive blocks are overlapping, and two consecutive blocks has an overlap of p. This is shown in the figure. This process can also be called as face image parametrization. The dividing of face image into blocks can also be called as blocks extraction. Feature extraction. The performance of the face recognition is highly dependent on parameters p and l. If the value of p is large, the performance of recognition is not much dependent on variations of l. Each observation vector is constructed with pixel values of each block. So even the observation vectors carry a dimension of L into W. Constructing the observation vectors based on the pixel values lead to less efficiency and reduction in performance due to the following two reasons. Pixel values are highly prone to distortion and sensitive to image rotation and highly depends on the background lighting conditions. Due to the large dimension of the observation vector, as they carry the same dimensions of the input image, this leads to the high computational complexity for the face recognition and the detection systems. These two factors affect a lot in the real-time applications where recognition and detection system operates on a large database. Feature extraction. In this model, KLT coefficients, which are also known as Karhunen-Leaf transform coefficients, are used to construct the observation vectors. The KLT coefficients provide features such as compression and decorrelation, which makes the observation vectors generated using KLT more viable than the others for constructing the observation vectors. In the images from the training set, vectors are formed by extracting the blocks and arranging them clockwise. The KLT coefficients are calculated from the largest eigenvalues of the covariance matrix of largest eigenvectors. The covariance matrix is constructed from the vectors with a mean mu. This mean vector mu is subtracted from the vectors corresponding to the each block of the image. So the eigenvectors of the covariance matrix are used to project the resulting mean vectors obtained in the previous step, which form the observation vectors. The next figure shows the observation vector constructed for blocks of the images corresponding to various regions of the face. So the upper part of the image shows the KLT coefficients for the right, starting from eyes and forehead in the middle and hair in the left. The bottom part shows for the mouth as well as the nose, with the nose on the left. Training the face models. HMM is trained by a set of images for face detection. These set of images consists of various frontal faces which are captured under various lighting conditions and various angles with respect to the image plane. An individual HMM model is constructed for each face in the database. The respective HMM model is trained with set of images of the same face captured in different instances. Each image in the database used to extract blocks which are used to construct the observation vectors from the KLT coefficients. These images are used to train the HMM model. Training the face images. The equation shown above, lambda is equals to a, b and pi, represents the HMM. This is initialized by segmenting the training data from top to the bottom with value of n is equals to 6 states. The initial estimates for the observational probability matrix P, which was explained in the previous slide, is obtained by using the observation vectors of the state corresponding to them. If the structure is left to right, then the initial values of A and I are already set. In the next step, Viterbi segmentation is used instead of the uniform segmentation, which is being used in other models. If the Viterbi segmentation likelihood is smaller than the threshold for the continuous iterations, the iterations will stop, followed by the initialization of the HMM. Baum-Welch recursive procedure is used to obtain the final parameters of the HMM. The flow chart illustrates the step-by-step procedure of the HMM, starting with the prototype HMM. So in this step, first we do the uniform segmentation of the image and then we initialize the parameters for the HMM, which is followed by the Viterbi segmentation. Face detection. In the first step of the face detection, if the image to be tested has more than one face in the image is clustered into rectangular windows and the face detection model starts by looking into those rectangular windows. The observation vectors for those windows are extracted and the probability is calculated for the data inside that window. As the size of the image is going to be large and to cover all parts of the face in the image, there is going to be a high overlap between each window in both vertical and horizontal directions. The probability of data inside each window is calculated using the Viterbi algorithm as the computational complexity will be less. The probability of any windows is more than the threshold, then that window is considered as a probable face detection. Due to the large overlap, to remove the false windows from being considered to be the probable face locations, windows around the current window with vicinity and with high probability more than the threshold are considered to be or classified as the possible face locations. This method of selecting helps in reducing the computational complexity as breaking the image leads to small observation vectors. The figure here shows the steps involved in the face detection. The first step would be the block extraction, followed by the feature extraction and calculating the probability using Viterbi segmentation and taking the decision by comparing it with the threshold if it has to be classified as the possible face location. Face detection. The images shown in the figure are used to train the system. In the images shown in the figure, the images are segmented horizontally using Viterbi segmentation. The 9 manually segmented images are used as the training set, which are captured under various lighting conditions. Face recognition. For testing the HMM, a set of images were used to other than the 9 images which were used to train the system. The images taken for testing have no background. As shown in the training phase, the blocks are extracted first and then the observation vectors were obtained to find the probability using the Viterbi recognizer. The highest likelihood model is chosen after calculating the probability, which is used to finalize the model for recognizing the unknown face. The testing model is shown in the next figure. The testing starts with the probability computation, block extraction, feature extraction, the probability computation, and also using the Viterbi recognizer to finalizing the model. This system is tested using the images from the MIT database as well as the Olivetti Research Limited database. Initially, the system is trained with 50% of the images available and tested with the rest of the images. Here we can see that the system starts with the block extraction and the feature extraction, followed by the probability computation for the overlapping windows, and also the maximum selection, which chooses the highest probability, and the model is finalized. Face recognition. The input set of images from the databases has images with different face expressions, different color, background, different hairstyles, and different eyewear. The success rate of this method is approximately 86%, which is more than the other methods based on the HMM model. The runtime of this method is also less, which is approximately 250 milliseconds, whereas it is 700 milliseconds for the existing techniques. The less runtime is due to the less number of computations, which is because of less number of observational vectors. The results are shown in the next figure. The images are crossed, which are failed as the system did not detect these images, whereas the other images shown in the figure are detected correctly by the system. Conclusions. In this paper, a face detection system using the HMM approach is presented. In this method, the extraction is done using the observation vectors, which are constructed based on the KLT coefficients. An efficient HMM-based face detection and recognition technique is proposed in this paper. The success rate of 86% of this approach and very less computational time can prove that this method can be considered for the face detection. Even with the high success rates in varying lighting conditions, backgrounds, and image orientation, this method appeared to be the most promising HMM-based approach which can be used for any face expressions and lighting conditions. Now I'm going to show a demo about the project. So here is the GUI representation of the MATLAB of the system. So initially I'm going to select the image. This is the data I have. Each folder represents an image with the different frontal faces of that particular person. So whenever I store an image into the database, I have to give an session ID for that. So in this step, I want to add the image to the database. So I'm giving a session ID of 2. Now I want to detect if the image is already present in the database. So in this step, I'm going to choose another frontal face of the same person, and then I want to know if the image is already present in the database. If you can see, the ID we entered for that image is 2, and the recognized ID says, and the system recognizes that ID as 2. This is my presentation for the project face detection using hidden Markov models. Thank you.